do neutron scattering, neutron spin-echo spectroscopy, and then look at domain motions in proteins. And now but first proteins. You basically all know about proteins, how the structure is. And when the research about protein structure was beginning, it was found that you have here alpha helices and beta sheets and this internal structure with amino acids inside. And if you look at this picture then of amino acids with a cofactor or a substrate here inside, that has exactly to fit at a specific place. Therefore, the function of the proteins, this lock and key model was developed to explain protein functions that mainly explains selectivity, that only very specific substrates work together with one protein. The problem with that was then that, like in this case here, I need the pointer, like here inside, it is very difficult for the substrate to enter exactly this position. And based on that, there was then another model developed that is the induced fit model, where the protein changes its shape that it allows the substrate to enter and that the product can then go off again. So we have there a change of the protein structure. Later, it was then found that proteins have a lot of dynamics inside. They are really dynamical objects with bond vibrations, side chain rotations, and also large domain movements. And based on that, the dynamics or the kinetics was explained by conformational selection. And that means that here the protein is always changing its shape, and the substrate is then binding when the right configuration was found. Today, this is also challenged and more complex models are used today, but in general, dynamics is included now into this binding. And what we finally want to understand are such complex motions like here this kinesin walk on a microtubule, where we have an ongoing binding and release of ATP and ADP, and then we get a very complex motion. With neutron spin echo, we cannot look at such a kinetic walk. What we can only do is look at equilibrium dynamics. But that gives us then the possibility to understand which motions are important and how strong they can be. And that is the general aim then why we do this science on proteins and try to look at domain motions. So in the following, I will just very shortly show ZACs and ZANs and then explain mainly the basics that we need for spin echo and how to evaluate the data then. I will show then unfolded protein ribonuclease. I will look at polyelectrolyte dynamics that shows very good what we need to do in these unfolded cases. Basically, I will first show this. And then I will show two examples for real domain motions where we have domain proteins. The first is phosphoglycerate kinase, and then our immunoglobulins. I just want shortly to point out here that all the calculations that I do can be done with JScatter, that's the program that I have written to calculate diffusion coefficients and how and what we measure in spin echo, also in quasi-elastic neutron scattering, to do the data evaluation of these systems. So let us begin with small angle scattering. You know this basically all that we have here a sample and we have a neutron beam, and that is scattered here, and then we measure here at the detector the scattering intensity. The scattering intensity is then roughly the square of the scattering amplitude, and there we see the Fourier transform of the scattering length density. And that can be then from electrons if you do X-ray scattering, or scattering length as a contrast from for neutron scattering if you do ZANs. How does this look now? So these are calculations for different sized proteins. This gray region here is a typical small angle neutron scattering region, where we see then here at low Q that dependent on molecular weight, we get more intensity. The real shape information is then given in this midterm range here, where we get something like this hump here for alcohol dehydrogenase, that is a tetramer. And at higher Q, then we go here to quasi-elastic neutron scattering, where we see mainly the incoherent scattering of the proteins and only the 10 to 20% coherent contributions. The difficulty for us is in general that these calculations are done for 10 milligram per milliliter, that then our D2O background is at this level here, which means that if we want to see more details of this mid-range Q range here, so really where we see shape, we need to increase concentrations to get there better data. Now, if we do spin echo, then we do this exactly in the small angle range. And here you see the old setup of the Jülich spin echo that was at this time here already at FRM2. This is a nice picture because here you see the main coils here in red and green here and here. And here in the center we have then the sample. The above picture here is already quite old, and we always used it here in our group to explain spin echo, we use the neutron spin as a stopwatch to measure small velocity changes. The main components are here the main coils, and we have here a pi flipper that changes the polarization, and here at the end the same, and we have here a pi flipper that makes an inversion of the spin. The main thing that happens is that the spin here then does a Larmor precision in the main coils, and this is returns then back on the opposite side. To explain how spin echo works then, I don't want to go into the details, but I want to change this explanation that we can split this here in up and down spins, and these up and down spins have different velocity in the main coils here, and therefore they arrive here at different times at the samples. So we get snapshots with a time difference in between. And that is then reverted again in the second part. And then we get an interference between these two patterns that we have. And in that way, we can measure directly a correlation function. That is the typical thing that we measure with Neutron spin echo. And that is the way then to detect changes in the configuration. So how does this look in reality more? So what happens then? So in small angle neutron scattering, there we make an ensemble and time average over such molecules that always change shape. And each of these configurations has then a different form factor. And we see then at different snapshots at different times with spin echo. That means here these different gray curves. We see directly the transition between these. And this in the correlation function looks then like this decrease here. And after some times, everything here is relaxed to the average. And then we see only the center of mass motion of this. So you see this also here, that it is always changing the position. And after these times, then we see only the diffusion, translational diffusion here. Now, if we look at a real measurement, then this is a bit more complicated. We measure here several Q values, and for long times here up to 200 nanoseconds. And here we can then see if we go to very low Q here, that corresponds to these positions, then we have only very small changes in the form factor. So we see only translational diffusion. If we go to higher Q here, that corresponds to this Q value here, then we see really the fluctuations here. So we need this low Q and the high Q to separate also diffusion and internal dynamics. Now, how can we then describe this internal dynamics? And already long ago, this was done all for polymers, and where the SIM model was developed that basically is then center of mass diffusion that is included here, and then normal modes here along the chain. In the SIM model, we have no explicit configuration because it's always self-repeating and always makes a Gaussian configuration. This is different for proteins. There we have explicitly one configuration, but we can also calculate normal modes. And then based on these normal modes, we can calculate how the scattering pattern is changing. And this can be done in a simplified pattern like this here shown, like the one here shown. But this can also done with Brownian diffusion in a harmonic potential. I don't want to show the equations for that now, but it gives a very similar pattern. And there we can even extract force constants and the relevant friction for these motions. How does it look in a simple case? So for proteins, then if we have a rigid protein, then we can calculate the diffusion coefficient here. And that contains here the diffusion tensor, that is a 6x6 diffusion tensor that has translational diffusion and rotational diffusion components. And if we look then at the effective diffusion, how this looks in general, and divide this here by the translational diffusion, then it starts here at low Q, we see only translational diffusion, and the increase here is then because of rotational diffusion. Here we can even get such strong peaks for alcohol dehydrogenase, that is a tetramer, so it has an internal specific structure, that we can get even peaks. In general, this levels then at high Q more or less to something here around 1.25, so the increase is just 25%. I already shown that the D2O background is quite high, and if you want to have really excellent data, then we need to increase concentration, and typical concentrations that we use are 25 to 50 milligram per milliliter for spin echo. So we have to account for the interactions and take these into account. This is in general done by this very well-known H of Q, the hydrodynamic function, divided by S of Q, that is the structure factor, and that is multiplied by the self-diffusion or the center of mass diffusion here. And the effect of that is that if you compare this here for spherical particles, this downturn in the structure factor, from that we can calculate the hydrodynamic function that is here at high Q lower. That is just if you increase concentration, then you get a slower diffusion, and that is modulated at low Q, and that compensates a part of the structure factor effect. So in general, here you see the comparison. The stitched line is without the modulation of the hydrodynamic function at low Q, so it reduces this effect. This can a bit be used to define the strength of the hydrodynamic interaction, because the models that we use here from the de gamma expansion are basically only valid for spherical particles, and we use it here for polymers and also for proteins. But we can use the radius of the spheres that we use here like a parameter that describes hydrodynamic screening. So if this radius goes to 0, that means just that we have no hydrodynamic interaction. Now, how does this look with measurements? So here shows 3 examples. The uppermost here, that is ribonuclease, quite small. It has no internal dynamics, at least not on the timescales that we measure. And then if you look at the effective diffusion, then the increase here is from rotational diffusion, and the increase here to top, here's the dynamic light scattering. That is exactly this H of Q, S of Q correction that we see here very well. If we do this now for flexible proteins, then we see that in the initial slope, that is the way to extract all possible dynamics and how it looks in the effective diffusion. We see at low Q here that this fits quite well. There we see only translational diffusion. This here is in the rotational contribution, but we see that it is different. And this is because of internal dynamics and domain motions, really. For alcohol dehydrogenase, it was here also possible to measure the long time diffusion coefficient. There you see directly the difference. We will have more examples from this. Now, if you look at this normal mood model that we have, then we can calculate how the displacements of the normal modes and the relaxation time contribute to the change in diffusion. And what we see then here, if we only measure diffusion coefficients in the initial slope, we cannot separate amplitudes here and relaxation times at the same time. We can only get an effective change. So now to our first example. Basically, this was motivated by intrinsically unfolded proteins, and we wanted here to see just if you take a polymer with charges and a large side group, do we see the same internal friction? And we used here the classical polyelectrolyte, polystyrene sulfonic acid, and that is neutralized in some parts here, but we have a large side group, but we have a constant backbone, only carbon-carbon bonds, and then here charges. But this is only partially true because we have ion condensation, and therefore the effective charge here is only 8% of the total monomer number. We can follow this then here with ZAX, where we see here for low salt the strong structure factor effect, and if we add then more and more salts, the structure factor is becoming smaller and smaller because the salt ions screen the electrostatic interactions between the particles. The typical thing that is done is dynamic light scattering that is shown here. That looks a bit confused at the moment because it's difficult to understand what you see. But with PFG NMR, we can measure the self-diffusion, and from the self-diffusion, we can measure or calculate the radius of gyration, calculate the overlap concentration, and now we can rescale this here. And if it is rescaled, then we see that this basically falls all onto one line here. If we approach here, then the size of the proteins become equal to the overlap concentration, that they start to touch, then we get here collective effects here. This case here, the lowest concentration is a bit different, that I will show you later. And self-diffusion goes down here. And we need to explain now this difference between self-diffusion and this collective diffusion. For that, we do Spinecho. That here's a typical measurement of these samples together with the dynamic light scattering. We do here combined fit. But it's a bit difficult to understand what we see, and that the fits here are really good. Therefore, I take just effective diffusion. I fit everything just with a single exponential that I get an effective diffusion, and then it's a bit easier to understand. At low Q here, we see the collective diffusion, and that is much larger here than the self-diffusion. That is interparticle interactions. At higher Q, we look then more into the polymers here, and there we see really segment motions here, and that we want to explain now. And for this, we first use this H of Q divided by S of Q correction again with an effective hydrodynamic radius, and that explains our upturn here to the self-diffusion with Q. The next thing that we need is now this segment dynamics, and for that we take just, again, the SIM model. That is a classical model that has here springs between the beads, but this does not explain everything here. Here's already a difference, but what's very nicely given here was the SIM model. If you look at an effective diffusion for larger Q, then it can be derived that it's linear in Q, and the slope here is only dependent on the solvent viscosity. Now to explain the last part here, this deviation, now we include internal friction, and internal friction is friction between neighboring beads. And that adds in the SIM model to mood relaxation times just a constant term here. And that explains then our decay from the no friction case to the case with internal friction that we observe. And this we can do now for several salt concentrations. And basically we see everything, every time the same pattern. At low Q, we see these collective effects, and then we see some segment diffusion that fits to the SIM model, and at larger Q here, there we see this internal friction. The general finding is here that we go here to larger salt concentrations, and we see here a larger distance here. That means we have stronger internal friction. Also here, this linear regime is much shorter because of the strong influence of this internal friction. And here we see the same. A bit different is this case here that was already visible in the dynamic light scattering. This difference here between self-diffusion and collective diffusion for dynamic light scattering is smaller, and we can only explain this here that a larger fraction of the counter ions is condensated on the chain, and therefore we have a smaller interaction between the chains. And that changes then just the pattern, and it fits more to something closer to this case here. What we in generally need that is that these hydrodynamic interactions are not zero, except of this case here where this hydrodynamic interaction radius is close to zero. All others show significant contributions from hydrodynamic interactions between polymer chains. Now we come to another problem. Now we switch from a polymer, a polyelectrolyte, to an intrinsically unfolded protein. Basically, we start not with an intrinsically unfolded protein. We use here a thermal unfolded protein, ribonuclease A. Ribonuclease A is a small protein, and it has a nice property that if you unfold it by heating, that is done here with several methods where you can observe this, and you cool it down, then you get no aggregation, and it really folds back to its original three-dimensional configuration and not to just an aggregate. We can follow this here by dynamic light scattering, CD spectroscopy, where we see basically always the same thing. Here around 60 degrees completely unfolded, and we can measure here structure factors that we need for the hydrodynamic interactions. And if you look at the Kratky plots here, we see also this change. So at 25, you have a folded structure, and if we increase temperature, then we see here then a different structure. This does not fold to a Gaussian chain. The structure is here shown. And this looks very similar to scattering patterns or form factors in a Kratky plot from rings, where you also have a maximum and then a decay to a plateau. And we can do simulations and show that really this pattern here is found because ribonuclease has 4 disulfide bonds that are still intact in the unfolded case. And there we see exactly this pattern because of these 4 disulfide bonds. Now, if you go to dynamics, we do again now the same thing as before. I show here just the spin echo pattern, and here for the SIM model. For the SIM model at low Q, we see then again only translational diffusion, and we see then this does not fit at larger Q. It's just too fast decaying. And here again, we use then internal friction to slow down, especially here this high Q moods. And what we find then here is an excellent fit then if we have the internal friction time around 9 nanoseconds. Here we find then that these 9 nanoseconds are double the time from the first mood of the SIM motion. That is the slowest mood. So basically in our equation here that determines the dynamics of the different moods that we use to describe the chain dynamics, we see that basically this internal friction is always dominating. And basically one can then assume that already this is not a free-floating chain somehow. This is already more a chain configuration that relaxes like an elastic chain, more like a rigid chain. One can also do this then temperature dependent, what we did. If you have then a fraction of the folded structure and of the unfolded structure, and can fit these contributions that are here, the black points, that fit very well to the other observations. And then we get different internal friction times that are shown here in an Arrhenius plot. And here we get then also an activation energy for this internal friction. That is here around 33 kilojoule per mole. And we can compare this to the structure of the amino acids, where we have here a peptide bond. Peptide bonds have something like a bit more than 60 kilojoule per mole if they do a rotation, but the carbon-carbon bond here has only 25 kilojoule per mole. And here we can imagine that the major contribution is coming from the carbon-carbon rotations around this atom, but also a fraction of the peptide bonds that we have here will contribute. So we get something in between. We did something similar than for the polyelectrolyte, what I showed before. And there we only have carbon-carbon bonds. And without salt, there we find a value that is very close to the 25 kilojoule per mole. And the reason for this friction is just that we have there asymmetric bonds that make dihedral motions. And in these dihedral motions, we have energy barriers that have to be overcome. And that seems to be the main source of this internal friction. So it seems not to be related to side chains. With that, I want now to change to domain motion. That was one of our first examples where we really observed domain motions. And here the phosphoglycerate kinase, the work of this is that it has here two substrates. Basically, it starts with ADP, also an diphosphate here, and here is a remainder from sugar. And the work is that one phosphate group is added to adenine diphosphate, that it becomes adenine triphosphate, and this triphosphate can then used in the body for delivering energy. It was already known from crystallography that without the substrate, there is an open structure. And if you add the substrate, then you have here a closed structure. We can follow this by Zanz. That is here our Zanz data in a Kratky plot. The blue is the crystal structure, and we have added then the substrate. Then we measure one structure, and without the substrate, we measure the other structure. And we see clearly the difference. And here we wanted then to model the configurational change. And that is done by normal modes. So we take these elastic normal modes that are the softest normal modes that we use here. That here is a torsion of the two domains. That is a bending that closes basically the cleft. The active center is here exactly then in the center of this cleft. And this here is a bending motion to the side. And if we combine these in the right way, then we can get an excellent fit that is shown here in the Kratky plot. With this knowledge now, we can go back to the structure and look at the center here. Here you see the phosphate, the sugar remainder here, and the adenine diphosphate here on the side. And we need here to have activity a very short distance between these two amino acids here. That should be around 3.5 angstrom. If you compare this to the crystal structure that's shown here, that is 11 or nearly 12 angstrom. That is not possible, even without the substrate. 11.4, that's still not possible. And also including the substrate, we have 8 angstrom distance between these amino acids, so there should be no activity, at least not in the static picture. And to solve this, we go now to the to Spinecho. I show here only the spectrum for 3Q values. That here is a low Q, where it looks again like translational diffusion. In this mid-range Q here, you see already that we have here exactly this change of slope that we want to see. This part here is related to the domain motions, and here we see translational diffusion. From this beginning here, we can then extract the amplitude and the timescale of these motions. That is here with and without substrate, 45 and 60 nanoseconds. And here you see the pattern of the amplitude that is increasing. We can now use again our normal modes and calculate then how the combination of these normal modes would describe these amplitudes. And from this, we can then extract mean as atomic displacements that are here 7 and 10 angstrom with and without substrate. And with this knowledge about amplitudes, we can now again look at the active center. So how do these modes change the distance between these two amino acids? That is then calculated for the different modes here. And there we find that basically here this normal mode 7, this position here, reaches already values around 5. So it's much closer than to the 3.5 angstrom that we need here. And if we now would combine in a statistical way all three moods and also the higher order moods that we cannot observe here, then we can reach here the 3.5 angstrom, where this center here is protected from water. And that explains us that these domain dynamics is basically the reason why we have activity for this protein. In a combined way, if you look, then this is all combining these motions here and gives a picture how this movements would look like in reality. Now, PGK is a very nice protein also to look at pegylation, just because we have these well-defined domain motions that are related to activity. And pegylation is used for drugs to improve lifetime solubility and stability for protein therapeutics, but it also is found that often it also decreases the protein activity. The reason for that is unknown, and there are some ideas that the active center is just covered and things like that. But this does not fully explain, because then we would see no activation at all. We use here now a matched pack, that we attach a pack here by a Malamute group here at this position, and we use matched pack that we only see the protein structure. We can then look also at the structure, again in a Kratky plot here, and compare it to the structure without attached pack, and that is very similar. So there's no big structural change. But now we want to look at spin echo again. Here we have our data. We have, again, our change in slope here at short times. The relaxation times don't change that much, so 60 and 45 nanoseconds again here. But here we can also look at the longer times and look at the diffusion, translational diffusion, and compare it to our H of Q divided by S of Q correction, and then we see that this exactly follows the line. So also in this complex case, again, of a domain protein with an attached pack, this is working. But we want to look at here domain motions, and the black line here now shows already the previous results again, with more moods to calculate this, and there we get a good description of our motions. And this, if you compare this with our red and green points here, then one could first think one could just scale the amplitudes up. But if we do that, then the protein structure would explode. So it's not just larger domain movements that we observe here. To explain this, we assumed then that the protein is trapped in a harmonic potential and makes more translational movements in this harmonic potential. And the polymer is acting like a spring in this case. And if we use this model, then we find a quite good description of our data. We use here this harmonic Brownian motion in a harmonic potential, and then we get also a force constant. And this force constant is around 8 piconewton per nanometer. The friction here is fixed to the value of solvent friction of the protein. But how can we explain this value now? And for that, we looked at a model of Biehl et al. That described how a polymer that is attached to a membrane is interacting with it. And there one finds that it acts with an entropic force that's described by this equation here. And we can calculate then also here the force constant for our RE. This part here is decayed already. That basically is a constant force constant, and also independent of molecular weight. And that explains two things. The independence of molecular weight explains why we observe here for 5K and 10K molecular weight matched pack the same values. And the other thing is this 15 piconewton explains roughly also the value that we observe here with 8 piconewton. So it seems to be that the polymer fixes the protein in a harmonic potential. So it does not cover it or anything like that, what is changing the activity, but it just fixes it at the given position. This does still not explain why activity is reduced. But if the polymer always is pulling and pushing at the protein structure, then one idea is that one has strain inside of the protein structure that reduces activity. But this is still a puzzle. Okay, now we come to the immunoglobulins. Immunoglobulins, you know all about. We have this Y-shaped structure with the Fab arms as Fc. The Fab arms have a binding site here where they bind to a pathogen, and communication with a receptor is done at the Fc part. And there are different types of immunoglobulins that is given here. It's difficult to get immunoglobulins in pure form. And in this case here, we used a powder from Sigma that contains IgG, but there we have then already four subforms. And where the majority here is 60% is IgG1 and 20% IgG2, which are a bit different here in the bonding. The IgG1 has here 2 disulfide bonds, IgG2 has 4 disulfide bonds. So there's a small difference. But in general, we assume that the structure is quite the same. The problem with these powders is that they contain a large fraction of dimers. You see this here in analytical ultracentrifugation, that we get here a second peak that exactly corresponds to dimers. And we also needed to explain our scattering pattern, the form factor here that we observe in SAX. We need a combination of monomers and dimers. And dimers are basically assumed that they form more dimers with the Fab arms, like it is shown here. Now, if we go to Spinecho again, there we see a very nice spectrum that is measured at the Jülich Spinecho instrument when it was located in Garching. Olaf Holderer did these measurements. There we see here nicely at short times that we have here this additional dynamics. And at longer times, we see nicely translational rotational diffusion. If we look at translational rotational diffusion here, then we get these points here, and they fit quite well again to calculations that we take monomers and dimers, combine these in the diffusion coefficient, and also include here the hydrodynamic interaction of structure and also H from Q divided by S of Q that increase here the diffusion value to the light scattering values that we have here. So this fits very well. Now we come to the more interesting short time part here. Here we take again this Brownian dynamics and the harmonic potential. That means each of our domains here is in a potential trapped, and where the spring, so the linker connection between the fabs acts as a spring. And using this model, we get here these very nice fits here. And here we get then as fit parameters the relaxation time of around 6 nanoseconds. The mean square displacements are around 4 angstrom. But more interesting is here the friction per fragment that we get, and that is roughly that what you expect if you cut the linkers and calculate the diffusion of a single fragment. So that is just friction with the solvent. The second thing that we get here is the force constant that is around 10 piconewton per nanometer. And this value corresponds then to an entropic spring that has the length of the linker region. And there we can also calculate here 10 piconewton. So this linker region just acts like an entropic spring for our fragments. At this point, from the long-time dynamics, we cannot access more, and it was always after these measurements that we did my dream to get monoclonal antibodies. And that was then possible with LINXS. And especially because we got our antibodies from NIST. And that is a very nice system. It's very stable. And we got large amounts that we can make really good experiments. And I show here just a sequence of measurements with the same buffer. That was what we decided to use here, this aesthetic buffer. And we changed here 40, 15, and 0 molar added salt. So we see here also in the structure factor that was extracted that without salt, we have here stronger structure factor than with salt, where we have a lower structure factor. So we have here structure factor. So the second thing that we can do here is we can use the form factors. That is shown here for at 35 degrees for the different structures. The structures are basically the same. There is no big difference visible here at this point. We can see here the comparison to this NIST PDB structure. That is an artificial structure. The linker region here is an artificial combination. And we see this difference here. What we do now is we try to fit our form factors. And therefore, we use some pseudo-normal modes, like it is shown here. We just assume that we have 4 possible motions. That is 2 bending motions in plane and out of plane of the motions. We allow a motion of single domains along the axis to the center of mass, and we allow a shrinkage of the linker region. And what we find then is here very good fits that describe the structure. In general, we find smaller structures here. The radius of gyration here of them all is an average around 5, whereas in this structure here we find 5.6. And what we see here is that for this structure here without salt, this seems to be more open compared to the other two here. So this is just a bit more open. We can use then our samples in dynamic light scattering. That is shown here. This stronger increase in dynamic light scattering with concentration is exactly again related to the stronger interaction. And if we extrapolate all of them here to low concentration, then we find that they go to the same point. So the diffusion coefficient is roughly the same. And we see that it is really a bit more than what we expect for the PDB structure from NIST, but that is expected. Now from this, we look at spin echo data again. This picture here shows the overall data, where we see here in this region mainly translational diffusion that looks in this plot like linear decaying function. And if we look now at the short time region here that is shown here, there we see again this fast decay on a 10 nanosecond time scale here with amplitudes. Here we want to extract again these amplitudes. And for this fit, we use now a model that has one contribution here for the short time and then just a long time effective diffusion, and that contains then all contributions from translation, rotation, and if we have slower motions there inside. And we can calculate that. With that, we get here excellent fit. We find here that the relaxation time overall is around 12 nanoseconds, and root mean square displacements are around 1 nanometer, and this does not change if we change the salt concentration. That's always more or less the same. The mood displacements here in this all enter here at this position. And for this fit, we use stretching movements. They go from the center of the linkers to the center of mass of each fragment and then are oscillating around this position, basically. This looks for all more or less the same, and the long time diffusion is then shown here. We did all these measurements for 15 and 35 degree. The change between these two sets of values is just because of temperature. And therefore, we try here first a viscosity scaling to the lowest values here. And then we see also that the temperature is not influencing these motions, because the blue points here for 2 different temperatures and the green, they all fall onto the same lines. Then we include translation and rotational diffusion. And the thin lines here, that is just translational diffusion. And here's the long-time part that fits exactly to the measurements of PVG NMR, where we measure long-time self-diffusion. Then we add here in this part the rotational diffusion, and that is the increase that we observe here. And that seems to be independent of the salt concentration, but still we have here a difference to our measurements. And for that, we add now an additional term for internal motions. As already mentioned, we cannot really discriminate amplitudes and relaxation times here, and therefore we calculate this just for an assumed relaxation time of 100 nanoseconds. And then we find that the additional amplitude here, if we take only bending motions, in and out of plane bending motions, then we find root mean square displacements of 2 nanometer with salt and around up to 3.7 without salt. And to explain this now a bit more detail, how these moves contribute, I show here calculated patterns, how these additional motions here would look up in the effective diffusion here. And there we see that rotations of the domains are the blue lines here, they don't contribute that much. The stretching movements that go from the center to the outside, they show here a characteristic peak at 0.05 that would show up exactly here in this region and have a minimum then later around 1. So here. If we would have strong contributions in these patterns here for the long-time dynamics, they should show up clearly here in this range. The bending in plate and out of plane are shown here in red and green, and they look more like the pattern that we expect from rotational diffusion. And that would lead then exactly to the shift that we observe here. And that was basically the reason why using for the fast motions, the stretching motions here, and for these long time motions, the bending motions mainly. Now, how is this correlated to the structure? If you look at charge and hydrophobicity, you find no significant changes here. But what we find is that this open structure here has the strongest contribution also to the dynamics. And this might be that just if you have a more open configuration, then larger amplitudes are possible. If you have a more closed configuration, then there is no space to have large configurations. And in that way, the static observation might be related just to the dynamics. And to clarify here, if there is more behind, one would really need computer simulations to see how the interactions change this behavior. Then the last question that is, why do we observe this? We have very specific structure and we have this separation of different modes. And just an idea is that the slow bending motions that we observe here are search motions to find a binding site at an antigen. And then the fast motion that goes along the axis of the fragment that attacks then the binding site and tries to bind there with a bit more force, and is not just waiting around until maybe it binds. There was a bit more an aggressive idea how this binding is done. We cannot prove this, it's just an idea why we observe this structure and these specific motions. And with that, I want to end this, and only very short summary that Newton scattering is really a non-destructive method that can explore protein structure and dynamics. And with that, I also want to thank all the people that contributed here, especially also the instrument responsibles from IN15 and JNSA that did all the measurements, and also LINXS for our project and NIST for these antibodies that we got here.